All right, welcome back to another episode of the Science Bros. This is our 5th episode, and because it is our 5th episode, we are going to have 5 science demonstrations in this video involving electricity and magnetism. Now, since this video is a little longer than what we normally have, I have included the timestamps for you here. You can click on these timestamps to go to any point in the video to view the demonstration, so feel free to go to one or the other. Or if you really are feeling adventurous, we encourage you to watch the whole video. I think it is one of our best, so thank you for watching, and I hope you enjoy. So our first demonstration here, we're actually going to generate a little bit of an electric field. The way we're going to be able to do this is actually by taking a PVC pipe here and a standard regular old aluminum Pepsi can. The can is empty, and it's been dried out and everything, so what we're going to do here is we're going to try and introduce a little bit of an electric charge, but just to show you what we're doing here first, I'm going to take the standard pipe here and hold it next to the can, and obviously nothing's really going to happen. But if I take a cloth here and I try to generate a little bit of an electric charge, what should happen if I hold the pipe just ever so closely to this can here, what should happen without touching, I should be able to make the can move. Let's see if I can bring it back. So pretty neat. Now let's talk about why this is happening. So to understand what is occurring here with our PVC pipe and our soda can, we have to understand a few basic principles. The very first thing we have to understand is what is matter, and matter is going to be anything that has mass and takes up space. We also need to know that all matter is going to be made of atoms. So for instance, here we have a model of a carbon atom. And we also need to know that an atom is going to be the simplest form of matter. It is made of protons, neutrons, and electrons. We know that protons are going to be the positively charged particles. Neutrons are going to be neutrally charged, so they're really going to be almost evened out with no positive or really negative charge. And electrons are going to have a negative charge. And we can see from our model right here that the protons are going to be highlighted in blue here in the nucleus of the atom. That's the densely packed center of the atom. We also can see here that we have neutrons, which are going to be highlighted in red here. They are also located in the very densely packed nucleus of the atom. And then finally, the electrons are going to be in gray here, and these fly around in what is called the electron cloud. They kind of fly around in these somewhat fixed orbits, but they kind of randomly move around as well. It actually is a very interesting topic to delve into, but we don't have time for that today. And then another thing we need to know is that when the number of protons equals the number of electrons, the atom is considered to be electrically neutral. You know, it is not positive or negative, it is just a nice neutral atom. But if we remove electrons, it can create an imbalance of charge causing static electricity. And that is actually what we have done with this example here. By rubbing the cloth on the PVC pipe, we are physically going to strip electrons off of the PVC pipe, and by doing that, we are causing this imbalance. We also need to understand that there are things called charge rules, and the charge rules are very simple for the most part. I'm sure you're probably familiar with them somewhat already, and just as a little bit of a reminder though, opposite charges are going to attract. So let's say here we have a positive particle and a negative particle on the left. Let's say that's a proton and an electron, and they are going to want to get as close to each other as they possibly can because those opposite charges have quite an attraction. The reverse of that is that like charges tend to repel. So for instance, we could have 2 electrons here on the right. These electrons are the same charge, and they are going to push each other away as much as they possibly can. It's almost like they don't even like each other. They try to repel from each other as much as possible. And then the last thing we have to understand is that there are multiple ways that charges can be transferred, but the one we want to pay attention to is induction. And induction is going to be the transfer of electrons through electric fields working at a distance or over a distance. So in this case, with the PVC pipe and the soda can, we are not actually causing direct contact. You know, I'm not taking the PVC pipe and physically touching the soda can. I am causing an electric field to act on these objects at a distance. Now, obviously, the distance is not that great. It's really only about an inch or two between the PVC pipe and the soda can, but regardless, we are still kind of generating this electric field that is causing an imbalance, and it is actually creating this attractive force. So in this example here, we have the negatively charged pipe in this example, and we have a sphere over here that has positive and negative particles. Now, if you'll notice, all the positive particles are on the left, and all the negative particles, or the electrons in this case, are on the right. This is because when we bring objects that have a charge, like the pipe here, when we bring them close to a neutral object, we can create what is called polarization. And for instance, in this case, we have a sphere. The sphere was neutral. In our example, the can was neutral, but when you bring an object close to it, what happens is the positive particles, or the negative particles, depending on what you're dealing with, but in this case, the positive particles in our diagram are going to get pulled towards the negative particles, because remember, opposite charges attract, and then you can see all the negative particles here are being moved to the right-hand side because they want to get as far away from that pipe with all those other electrons or negative particles. They want to get as far away from each other as possible. And that is actually really what's happening here, is we're generating a little bit of this attractive force. So we're basically, in our example with the PVC pipe in the can, we are creating this positively charged pipe because we're stripping electrons away from it, and we're bringing it close to this neutrally charged soda can. And by doing that, we're creating this polarization effect, which is then creating this attractive force between the protons and electrons, and that is why the PVC pipe can pull the can across the table without actually physically touching it.
Here are the science bros back at it again, and we're continuing with our electricity and charge demonstrations and talking a little bit about electric fields and current and simple circuits. We have a few more fun things in store for you. So what I have here is a little electroscope. What we have is a ball with a rod on it, all metal, and at the end we have two pieces of aluminum foil down there, or two just little metal strips. It's not really imperative that you have exactly aluminum metal, but it's just two little light metal strips down at the bottom. And if you recall the can from the can rolling, what we did is we stripped some electrons off, and we were able to use that to create this electric field that pushed or pulled electrons in different directions. Well, if I put this up here like here without a charge on it, then nothing happens, okay? Nothing happens at all. But once I strip some electrons off here, okay, strip some electrons, okay, now what we have is a positive into this pipe. It's an insulator, so the positive charges are there, and we stripped off some electrons. And when we put this close, okay, what we're going to do is we are going to attract the electrons that are in this metal. And since this metal is a conductor, the electrons will travel up to the end of the metal rod and into the ball there.
Wingardium Leviosa.
So now we have a cluster of more electrons than protons. So this is got an overall a negative charge. This because of this positive charge. Okay, I'm inducing. It's called induction. I'm inducing a negative charge in the end of that ball. Well, why are these strips moving apart though? Well, overall, this is neutral. That piece of matter in there is neutral. So if I pull some extra electrons up here to make this negative, because this end is positive, what charge is the bottom now? The bottom is positively charged, correct? Well, like charges repel each other, whether they're two negatives or two positives, they will repel each other. So by pulling the electrons up here, I am causing a temporary induced partial or positive charge, a temporary positive charge at the bottom. And since like charges repel each other, the two little pieces of aluminum foil will spread apart. But as soon as I remove this, right? As soon as I remove this, the electrons, they don't want to be near each other. They go back to where they wanted to be, making it neutral, so the foils go back to their original position. So what I can do is make these things dance by putting this close, moving it to and close and further away from this, by creating the temporary charge on the top of that.
For our next demonstration, we have a couple simple circuit boards set up here. So we have one circuit board here and one here, and there actually is a little bit of a difference between the two. So we look at them on the surface, and we see that we have two light bulbs on each board, and they are both lit up. But I want to highlight the difference here is that there are two types of circuits that we have demonstrated here. We have a very simple type of circuit, which is called series, and we have a little bit more complex type of circuit, which is called parallel. And there are advantages to each, but just to kind of highlight the difference here, you can think of our series circuit here as like a river that only really has one path to flow. So for instance, you could think of electricity as water flowing through the board here, or water flowing through a river. And essentially, the water only really has one path, or the electricity really only has one path. So we are supplied our power from our power supply here. It is moving through our board, and it is going to pass through this light bulb, and then it's going to pass through this light bulb, and eventually it'll make it all the way back to the power supply. Now with series here, everything really only has one path to flow. What I mean by that is, if you disconnect the circuit or you break the circuit at any point, so for instance, if I take this light bulb here and I unscrew it, then what's going to happen is both lights will go out because I have broke the current, or I broke the circuit. And you could think of it like damming a river. If you dam up a river, then what's going to happen is the water is going to stop flowing. So it's essentially kind of what I've done here is I've stopped the flow of electricity, but if I plug it back in, I've completed my circuit again, and then both lights will turn on. If we go over here to our parallel circuit, then what you're going to see here is that obviously this looks a little bit more complex. There's much more wiring going on than with our series. But the nice part about our parallel here is there is actually more than one path for the river to, or for the current to flow. Think of it like a river. There are such things as meandering or branching rivers. Basically, these rivers have multiple paths where water can flow. And it's very easily highlighted here that if I unscrew one of these bulbs, the other one will stay on because there's another path for the electricity to flow. So I can easily plug it back in, and they both are on. I could even do the same thing with this one, and that one will stay on. The nice part is here that there's multiple paths for the electricity to flow. This is very useful in terms of housing because, for instance, if you have a light fixture, you have a chandelier or whatever it may be, where there's multiple light bulbs plugged into it, if you have one light bulb go out, well, you don't want the whole thing to go out. That'd be very counterproductive. That'd be kind of a waste. So the nice part is that we can wire things in parallel. That way, if one light bulb goes out, then that means that they don't always go out. Sometimes, though, if you think of Christmas lights, if you've ever set up Christmas lights on your house, sometimes those are wired in series like this, where if one pesky bulb goes out, then the whole thing goes out, and that's just a pain. So it's much better in terms of wiring, in terms of electricity and lighting, that we have parallel circuits instead of series. In this demonstration, what we're going to do here is actually have a little bit of fun with magnets and iron filings. So we just saw some demonstrations where we could kind of generate this electric field, and this electric field could cause an interaction between objects. We just saw an aluminum can move, and we just saw our little device here, and we saw a little bit of the aluminum here move a bit once we introduced an electric charge. What we're going to do here is, instead of creating an electric field, we're going to create a magnetic field. We're not really going to create a magnetic field. We're actually just going to take advantage of the fact that these magnets already have a magnetic field. And these are actually very powerful magnets. And what we're going to do here is we're going to demonstrate kind of the same effect here, that we can cause a little bit of an interaction with these objects over a distance. So I'm setting my magnet inside of this container here. And what I'm going to do is take my iron filings, which is basically just a really nice fine powder. And I'm going to take my iron filings here, and I'm going to introduce the magnet here, and kind of notice what starts to happen. Oh. If you look at that, you'll notice that this fine powder of iron filings has kind of started to cluster around the magnet. And if you look really closely there, you see how a lot of it starts to bend up and kind of move in this curved direction here. That is because these magnets have a magnetic field. And magnetic fields, they have lines that look kind of like parabolas almost coming out, and they move around and they loop back into the top of the magnet. So what you're seeing here is actually a visual representation of something that we usually cannot see, and that is actually the magnetic field lines that are moving or that are surrounding this magnet at all times. The Earth also has a magnetic field. Thank goodness the magnetic field protects us from a lot of solar radiation and ionized high-energy particles. So that is just a little bit of fun with magnets. And you can see that instead of an electric field, now we have an example of a magnetic field, and kind of a cool example as well. And then the nice part is, if you take your magnet here and you remove it from the iron filings, or you just get it far enough away, what should happen It turns back into a powder.
Hello, welcome to the next exciting demonstration from the Science Bros. And we are looking at a Tesla coil. So without going into too much what a Tesla coil is, it's a transformer. So if you look at a pole near your house, you might see a transformer. Not like this. They're different. They're definitely different. But what a transformer does is can take high voltage, like power coming in from lines, and step it down to a lower voltage. So that's what a transformer does. It takes a different voltage and makes it a different voltage. So if in the terms of getting it to your house, you have 110 volts in your sockets and things like that. It transforms high voltage. When you send electricity over lines, you have less loss if you send it in high voltage situations. But you don't want the high voltage situations in your house for safety's sake. And so what you do is you have a transformer that will change the voltage. Well, this is a transformer. It is not the same type that you'll see near your house. Maybe I should name this Optimus Prime because I love transformers. So this transformer will take basically the 110 voltage coming out of this socket, and what it's going to do is it's going to change it to a couple thousand volts. Now, this would normally be dangerous if you had any amount of current going through it all. But the currents are going to be very, very low. So high voltage, low current situations, it's still a little bit, you need to be careful with it, as any device such as this, but it is not as dangerous as if you had more current. If you have more current, it is absolutely a very dangerous situation. But it's taking the 110 voltage and turning it to a couple thousand voltage. And you want to think of voltage as your ability to push the electricity. Current is the amount of electricity. Think of it as a flow of water out of a hose. If you have a lot of flow of water, that's a lot of electricity flowing. A little flow, that would be a little. The pressure is the voltage. How much is pressure in your hose? If you hold your thumb over the hose, then you can build up pressure and you let a little bit go through. That pressure is going to shoot the water a far way through the air. This voltage, high voltage, is the ability to push the electricity to places it doesn't want to go. So here, you're going to see this. And because the voltage, the pressure is so high, it will send it through air. It will send the electricity through air. So what we're going to do is we have a lightsaber, and we are going to light it up without touching anything with this Tesla coil. Ready? All right. And this is the moment we've been waiting for. It's going to be electrifying. Here we go. There we go.